The second derivative of parametric equations seems like it would be straightforward, but there's a little catch to it. So there's a lot right here that explains how to do it, and in my best explanation, I'm going to launch into a post-it note explanation that you don't have to write. I've had a hard time personally wrapping my mind around it, just being transparent, kind of like this post-it note. You can see a little bit of what's behind it. And had a hard time wrapping my mind around why this is. So I'm going to give you the best explanation that I have, and it's going to be a little bit awkward, but we're going to go for it. So if I wanted to find the derivative of a parametric equation, a set of parametric equations, first of all, I'd be given x of t equals something and y of t equals something, which means that x is a function of t, we'll call it time, and y is a function of time. So if I want the first derivative, I need to find, well, dy over dx, which is fine, but in order to do that, I'm really going to be taking the derivative of y with respect to its variable, so it's dy over dt divided by dx over dt, and that's what I've really found. So that's my first derivative. You can write it this way, you can write it this way. This way's a little shorter. Well, if I want the derivative of the derivative, then what I've really done, this is going to start looking like that, what I've really done is taken, well, the derivative of the derivative. Okay, so when this is that. This is not quite that, but we're getting there. Okay, this is an alternate explanation. This is my best verbal explanation. So what I want to do is take the derivative of this. Well, keep in mind that the variable we're really dealing with, like all of these are functions of t, the variable that we're really dealing with is time. The independent variable for this and for that is t. So what I'm really going to do is take the derivative with respect to time of this, but because of the chain rule, I would multiply by the derivative of this inner part, and this is where things get a little funky, and I have a hard time explaining why this is, but the derivative of this inner part with respect to time would be dt over dx. Okay, this is where, this part might be a little clunky, but we're going to keep moving forward. This would be the derivative of your derivative, okay? And then instead of multiplying by this fraction, let's divide by its reciprocal. So basically, we have a few options here. We could just remember this, which we will in the process of doing it. If it looks a little weird, don't panic, we'll get back to it. Or we could sort of remember this process, which to me is a little clunky, but it's the best explanation that I personally have, and there are others. You could search for it. You could go to YouTube and type second derivative parametric equations, and you'll get lots of explanations, and they make sense to different people. Okay, so anyway, this is it. This is the second derivative. So we're going to come back to this. If that made no sense, don't panic. We're going to apply it. Whether we understand it or not, we're going to apply it, doggone it. So first, let's find the slope and concavity of that point for that curve, the curve given by this. So let's just find the slope, okay? Let's start with the slope. That's the first derivative. That was the previous lesson. We can do that. We're going to do it in green, so here we go. I don't know why I'm singing it like that. The dy dx is the derivative of the y stuff, so negative 1/4 t, divided by the derivative of the x stuff. The derivative of that would be 1 over 2 square root of t, 1 over 2 square root of t. And that is my first derivative. So far, when they ask about concavity and that involves a second derivative, I haven't even had to delve into that because I'm just dealing with the slope at a point, okay? So I'm going to simplify this just a little bit more and treat it like what it truly is. I'm going to call that negative t over 4. That's the numerator. And we're going to divide by this, which means we multiply by the reciprocal, which would be that. And that is going to give me, well, that's t to the 1, that's t to the 1/2. That's going to give me t to the 1.5. So I have negative, oh, by the way, reducing 2 over 4, so 1/2. T to the 1.5. That's it, okay? Beautiful. I love it. I think it's great. Well, I want to find the slope at a specific point. And if I'm going to find the slope at that specific point, then I need to, well, find the slope at a specific point. And that's going to happen at 2, 1. So you might think, well, I'm going to plug in 2 for every x and 1 for every y. Oh, that's fantastic. But what I really need to know is what? T value, because this is my derivative. This is my first derivative. And if you're like, whoa, there's too much in this lesson already, I hear you. But what's really going on is we talked about the second derivative. There it is. And we haven't even gotten to it yet, but we'll come back to it. Someone just opened my door and then closed it. I don't know who it is. So what we're going to do is find the t value where this coordinate takes place. So I'm switching colors here. We're going to go to purple. I knew that's what you were thinking. So the x is 2. So x is 2, which is the square root of t, which means, awkward arrow that just sends me horizontally with my work instead of vertically. That means that t equals 4. And I hope that that's true because I'm going to test it with this one. If I have time on like a free response question, 1 equals 1 is the y value, and that equals -1/8 t squared plus 3. And we'll do a little bit of finagling here. Let's subtract 3, gives me -2, multiplied by -8. It's going to give me 16. And that is equal to t squared, which is going to give me 4 equals t. So yeah, we found t. Now that we know what t is, I don't need to plug in a 2 for x and a 1 for y. I need to plug in a 4 for t, like we found out what it is. So we're going to do that. So -4 to the 3/2 over 2. Okay, let's do this. Square root of 4 is 2. 2 to the 3rd is 8. So we have -8 divided by 2, which is going to give me -4. All right, fantastic. We have answered the first part of the question. We still haven't talked about concavity. Still haven't come back to this ridiculous idea that started the video. And let's do it. I was about to say, and someone's trying to come in my classroom. All right, let's do this thing. I want the concavity, which means I need the second derivative. So if you're thinking, I'll just take the derivative of this, no. Okay, now it's time to get down to the application of this. Whether we fully understand it or not, I keep pulling out this Post-it note and slapping it down and moving it away. I want to take the second derivative, which means I'm going to take, not the derivative of the derivative necessarily and leave it at that. I want to find let's look at what's going on the end of this. The derivative with respect to time of dy dx. This is dy dx. Okay, if you want to make it a little bit easier to deal with, you can call it -1/2 t to the 3/2. That's fine. Simplify it a little bit if you want to. We're going to take the derivative with respect to time of this, and that would be the derivative of that. And then we're going to divide it by dx dt. Well, dx dt was the derivative of the x stuff, which we already found. So there's a whole lot of random pointing going on. So here's what's going to happen. We're going to find the second derivative, which means we're going to find the derivative of the derivative. And I'm going to write just a little bit too much here, just for the sake of the first example that we're dealing with. -1/2 t to the 3/2. And then we're going to divide it by dx dt, which is simply the derivative of x with respect to time, and that's the variable that x is dealing with anyway. That's the variable that determines the x value. And so we're going to take the derivative of that, which we already did, so we're going to do that. And we're going to just keep going with this. Now, I do want to determine the concavity, which means I need to decide if the concavity is up or down by plugging in the appropriate t value, but we'll get there in a minute. Let's not get ahead of ourselves. So I need the derivative of this, so that would give me -3/4 t to the 1/2, all divided by 1/2 square root of t. Let's keep going with this. So we have -3/4, I'm going to call that t to the 1/2 here, and we're going to multiply it by 2, t to the 1/2. We'll put that over 1 just for fun. Gee, wasn't that fun? And then that gives us, well, t to the first in the numerator, 6/4, so that's 3/2. It is negative indeed, and that is 3/2 t, -3/2 t. Okay, so we just simplified a few things here. Backing up briefly again, just for a moment, let's see what's happening here. We took the derivative of the derivative and divided it by the derivative of the x part. Okay, now, running out of room, no. We're going to find the concavity, and we're going to do it in this tiny little corner here, and here's how it's going to happen. I want the value of the second derivative at 2, 1. Now, you could say it's at 2, 1, and you wouldn't be wrong. You could also say that it's at t equals 4 because at 2, 1, t is equal to 4. We found that out on the previous part of the problem. So negative 3 over 2 times 4 is going to give me negative 12 over 2, so negative 6. And that means, determining the concavity, the graph is concave down. Let's keep going with this explanation. With a slope of negative 4, going back to this thing, at the coordinate 2,